Okay, so welcome everybody. So before we begin, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. And today we are very fortunate to have Osvaldo talking to us about high performance computing. Osvaldo Espin-Garcia is a Principal Biostatistician in the Biostatistics Department at the Princess Margaret Cancer Centre. Osvaldo earned his PhD in biostatistics from Dalla, and is now an assistant professor at the Biostatistics Division as well. Osvaldo's research interests lie in developing novel methodologies in statistical genetic epidemiology, design analysis of two-phase studies, microbiome data analysis, and joint models of longitudinal and time-to-event data. So with that, I'm going to turn it over to you, Osvaldo. Thank you.
Thanks, Aya. Thanks everybody for the invitation. I'm going to start sharing my slides right now. Let me know if you are not able to hear me well, or if I'm not being, my connection drops or whatever. So I'll be talking today about high performance computing, and I purposely label it as 101 because it's really really introductory. So, despite that, it's mainly to get people more familiar with the concept of high performance computing and give some pointers hopefully along the way. So I'll be, I guess, monitoring the chat and please feel free to unmute yourselves. I think you should be able to, but if not, let us know, to ask any question along the way. So you should be able to see my slides. Let me know in case you don't. But I'm going to get started. Okay, so yeah, as I said, so the learning objectives of this session today hopefully will be, for you to first and foremost introduce the scope, utility, and capabilities of high performance computing systems. More specifically, I'm going to talk about three main relevant topics. I'm going to spend some time talking about, job scheduling and monitoring. I'm going to explain what that means. How you actually use software and libraries in HPC systems, and some pointers, mainly some guidelines, if you will, about data creation and management. And along the way, and also at the end, I'm going to provide some resources for you to do some independent learning on HPC. In particular, at U of T, I'm going to highlight some of these along the way as well, but also resources that I've found that could be useful. Okay, so I guess if you're here, I hope you fall into either of these categories. So you are either completely new to HPC, which is great because this is the right place to be. I'm gonna hopefully start initiating people and tell you, okay, it's a great thing and you should learn more about this. You may fall in the second category, which you may have some experience with HPC, but you may want to, find, or you may want to look for some useful pointers. And I'm hoping that I will be able to give you at least, one or two along the way. But if not, maybe it will be helpful for you to reinforce what you know. And if you don't fall into any of these two categories, you may just, okay, seem like an interesting thing to do today, which is also great. You're, very welcome. And okay, so that's about the intent of what this workshop is intended, or this talk is most intended for this kind of audience. Anyway, just moving on, I guess first, what is HPC? And I just put this image here, but this is kind of like what you would expect, or what people are selling high performance computing facilities or supercomputer facilities. These super shiny with all these light buttons and so on. And very state of the art, very modern, etc. In reality, this is your actual high performance computer, and I'm not saying that it's wrong, but sometimes we have these very high expectations, but in reality it's sometimes a bit more modest, if you will, maybe with not as many shiny and colorful buttons, but nonetheless super helpful. And this picture here is from the Niagara supercomputer of U of T, which I'm going to start. Many of the examples will go back to this specific system, although Also, I'm intending to give a broad or a general sense of things that could work in pretty much or are common to many supercomputers or high performance computing systems. So yeah, so I'll get into that in a moment. Okay, so in brief, so what's a high performance computer? What is that exactly? Well, the idea is this practice of aggregating computer power. And this, what I mean by computing power usually is measured in things called flops, which effectively stands for floating point operations per second. So right now, most, the fastest or the most powerful supercomputers lie in the peta scale. So they are able to do peta. I don't even know how many zeros that is, but that's a lot of zeros per second. So the idea here is to cluster or to aggregate these many small computers, and that's why sometimes people refer to these HPC systems as clusters, because that's effectively what it is. They put together many smaller computers, and they live in these networks. So effectively, each of these computers is called a node. That's kind of the jargon in the field. And the idea is that these nodes communicate using a dedicated network, that this is actually much faster than your regular cable. Is actually super fast infrastructure that allows the nodes or these multiple computers to communicate to each other. And here there's some figure that I got from the Wikipedia about effectively how they interconnect to each other, and effectively you could transfer data and communicate from one computer in the node to any other computer in the node by using all these these dedicated networks. And there are many different architectures, but this one kind of resembles this idea of a torus where kind of everything is interconnected by these loops over here, right? But again, there are many other different architectures available. And the idea is to deliver higher performance than just if you were to only use one single computer or your typical workstation. And also the aims to solve these much larger problems in different fields, science, engineering, or even business. So okay, with that, just briefly mention some applications. Mostly about the fields: quantum mechanics, weather forecasting, molecular modeling, astrophysics. So, but you name it. So they are very prevalent in the sciences. Effectively to be able effectively any problem that can scale or that has some features that can be scalable by aggregating computer power are you can throw HPC at those. So here in this slide, I want to briefly say why should we use high performance computer in the pros side. Well, I guess the main one, or the first one that we should all I guess hopefully everybody's interested in, is reducing the computational time. So problems that would usually take you weeks, if not months, to perform with using these HPCs would maybe take you hours, right? Or maybe days. So that's kind of the hope, right? So to reduce the computational time. Of course, along those lines, of course, increase CPU capacity. So why you want to increase CPU capacity? Because maybe you want to increase your model resolution, right? Maybe throw more parameters at your problem, or increase the number of scenarios, right? So maybe you want to explore many more scenarios that you are capable if you were only using your single computer. So that's another possibility how you want to increase the CPU capacity, but also increase memory or even storage, right? So you want to aggregate larger data, right? You have maybe the data from different centers. I don't know, you want to put them together, or in general, so just solve bigger problems, right? Maybe put more data together, and you want to your computer alone doesn't have such big storage. But I mean, maybe on another important point is that HPC can actually tackle otherwise unfeasible projects. And on that note, I want to just point you to this image that some of you may recognize from, I think a couple of years ago. This was the very first image of a black hole. So if you may remember this was in the news, highly covered in the news a couple of years ago. And interestingly enough, the way they use this, they put together this image, it was through the use of several HPC facilities, I think all over the world. Actually, Niagara, which is the one supercomputer that I'll be talking, referring to through the talk, was actually part of one of the systems that helped to put some of this data together. And of course, some cons on the con side here, why may not be that interesting to use HPC or maybe challenging. Of course, there's a relatively steep learning curve that hopefully this workshop will help to get around that part. So I'm giving you some initial steps towards that. And other potential con is that it's largely do it yourself. So many of the things are not so much out of the box. So you need to to learn how to do certain things, like compile some code in some instances. So it may not be as friendly for, it's not your typical workstation in the sense that it's mostly command line. So the interfaces may not be as friendly or whatnot, but many things require the user, a good involvement. But if you circumvent that, I think it's a great tool. I guess maybe lastly, these are typically shared systems. So and this means that there's some planning needed. So contrary to your typical workstation, it's only dedicated for you, and you are the only one using it, and you know how to run and when to run and what to stop, etc. So these systems are typically shared by many users, hundreds, if not thousands of users. So it requires that you kind of have some planning ahead on what you want to run, and if it doesn't run, what you will do, because you need to wait in some instances for it's not as dedicated as your workstation, of course. So yeah, that's on why using HPC. Hopefully this is convincing enough for you, but if not, we'll keep going towards working towards that direction. So okay, so just to get started, I'm going to talk a little bit about SSH, which is this secure shell protocol, which the idea is that it's a way to make a connection through a non-secure network to make it secure. And in the Windows system, there are a few programs that will allow you to establish these SSH connections. Anywhere where you see this blue here, you can click on them when you get the slides. So it will take you to these websites. So you can use these two software to establish SSH connection towards to one HPC. Or if you're a Mac or a Linux user, you can use something, terminal, which comes out of the box, so you can establish the connection using just your terminal. Okay, and then how to connect. And here I want to mention that this cluster, these supercomputers, can usually be accessed over the internet, although that's not always the case. In some cases, certain centers only allow the users to access the supercomputers through the local network. So, for example, maybe some of the hospitals won't allow you to reach the HPC systems using the internet, but you have to be locally within the hospital facilities and use the actual network in there. I mean, nowadays it's much simpler because you can use something like a VPN, and it acts as if you were in the local network, even though you are on the internet. But that's that's kind of how you access these systems. And kind of to get started, you simply type something like SSH, either in this mobile external on this PuTTY. I think in PuTTY you have a bit more of a graphical interface, but if not, the idea is to kind of establish a connection using SSH, username, and a host name. So this would typically be, in the case of Signet, kind of signet.utoronto.ca or something along those lines, which effectively is kind of an IP address, and username. Of course, in many of these instances, you need to have a username created for you. So that's how you get this username here. And there are other common syntax to access this. Here I'm putting ssh.y or ssh.x. That effectively what this allows you to is to establish some forwarding. You can establish some graphical interface with your computer and the cluster. And if you're on Mac OS or in Linux, and man, which stands for manual SSH, will give you lots of more options. And this is a really powerful command that can make many other things. But in kind of the simplest case is something just like this. And I really always encourage people to use their manuals or look at the manuals for kind of have a better understanding of some of these commands. Okay, so hopefully up here is everything is clear, but again, if not, please feel free to put questions on the chat or just mute yourselves. Okay, so here I think it's very simple. I just want to here illustrate kind of what the basic environment or a HPC looks like. So over here you have a user and you have your kind of your own computer, and then you throw this SSH command in your computer, and that will effectively connect you to what is called a logging node, which in this case is represented here by this computer, which you can imagine is one of those black stacks that I showed you earlier. And what this allows you to is just this is kind of your front end to the system. And oftentimes you can do a bunch of stuff in these logging nodes. Kind of explore what files you have in there. Sometimes it may even allow you to to communicate some files or put some files between your computer and the shared disk, for example. It will allow you to do that sort of connection, but it will also allow you to maybe throw some to throw some jobs and be able to use this called compute nodes. And then here you'll see this additional file server, which effectively what this one does is it kind of manages all the files and kind of takes commands from all these other logging and compute nodes to kind of store things in disks and kind of helps with the behavior of how files and files everything is stored in these shared disks. So yeah, hopefully this is kind of the idea. This is a very basic environment. Of course, there are other things that could be added here, but kind of for the sake of today, this is kind of the basic infrastructure that I'm talking about. And of course, within these compute nodes, there's some network within them that allows them to communicate among each other. Okay, I think that's the idea. So I just want to spend here one slide on shell scripting. Why? Because for most HPCs, so this is the one interface that you're going to be interacting from what you want to do to the system. And it's important because well, allows you to do things like interact with the system by itself, and for the most part you can get by using these basic commands. I don't know if you were here for some of the previous workshops, but we're talking about these commands, and again, if you don't know what they mean, this is kind of a very simple and basic way to read your files or move to different directories and so on. So hopefully you're at least vaguely familiar with these commands. So again, ls to kind of list file, whatever is in the present directory. cd will allow you to move between directories, and mv here is to move files between directories. cp kind of similar, but instead of moving them, you're going to copy them. pwds is tells you what's the present working directory. So the idea is how to so what's in there, what's in the system, how to move things around, etc., how to move between directories, etc. In case you are not very particularly familiar with shell scripting and the sort, so these are some intros and tutorials that can help you to get to familiarize yourself with these ones, and which again I will highly encourage you to learn a little bit more about these, at least the basics, to be able to before getting into HPC or while you're doing HPC. I think that's will be also important. Actually, you need this kind of knowledge to feel more comfortable about that. And again, HPC is, in case that this part wasn't clear, is mostly a command line interface, at least for the most part. So there may be some graphical ways to access it, but for the most part, is you have just typically this black screen with a prompt on it. Okay, so I also want to spend this one slide talking about shared versus distributed memory, because these concepts come handy later to understand how you want to run jobs and perform tasks in an HPC system. So here first, this first the image here on the left, it talks about, shared memory, in which you basically have, a bunch of CPUs here. And as the name suggests, they all share, one here piece of memory, and they are all kind of interconnected to them and so on. So this is what and here by memory, I'm really talking about, these fast access memory, like RAM, like, your rapid access memory. So of course, here, when I talk about memory, I'm talking about that as opposed to something like storage, which is more long-term and so on. So why I'm making this distinction? Because these memories, things like R, for example, whenever you store things when you create data frames or when you create any objects in R, all those are typically stored in these rapid access memory, so in RAM, right? So this is kind of the first architecture that most modern computers these days have, at least 2 CPUs, if not 4 these days, and they all share the same memory. Okay, so this is kind of what you have in your typical workstation, and that contrasts with something that is called distributed memory, in which, in this case, you would have, a CPU, and this CPU has its own dedicated memory, and you have, maybe multiple of these guys, and so kind of what is stored in here is not necessarily what is stored in here. So you have, in case you want this CPU to access something that is stored in here, needs to go through this interconnection, whereas in here, because every CPU shares some of the memory, is really fast to access them, right? So each of them has, kind of their pros and cons, but in HPC systems nowadays is mostly kind of a combination of these two. So you have these interconnection where you have multiple CPU, perhaps, each of them with, their set of shared memory, but you have many of these sort of structures, right? So it's kind of like you can very easily think of a combination of these two. And that's what most HPC systems are configured in this way. Okay, so hopefully that was okay. So, okay, I'm just, gonna switch gears a little bit here towards job scheduling. So, okay, you have access to your cluster, to your HPC system, and then you want to start, doing something. Okay, so for the most part, as you remember that image on how the structure of the system is, you're going to start in a logging node. Well, typically logging nodes are really not designed to carry large computations, right? So for that we have the computing nodes. So the idea is how you kind of let the system know that you want to carry out these kind of larger, more complicated computations, right? And you want to access certain amount of resources. So okay, that's what job scheduling is for. So, and I also mentioned, right, this is a shared resource, right? You're not the only user in an HPC system. There are many different users with many different needs. And of course, you need to ensure or enforce that, there's a fair use of what is available on the resource available in the system. Well, I mean, for that, we need something that is a scheduling tool. And this scheduling tool will take care of that. I'm going to talk about more detail on the next slide, but there are multiple scheduling tools that effectively allow you to do this kind of shared use, or being a fair use of the resources. And these are the names of the tools. In this talk, I'm going to focus mostly on Slurm, just because I guess in the last 5 years or so, many of the kind of academic clusters have moved towards Slurm, which is open access. And although there are many other ones, PBS Torque, which is an older one, HGE, LSF. I think this one is developed by IBM. And here the idea is just that many of these have different syntax, but the idea is the same, or have similar purposes. In fact, people at Slurm actually put together this Rosetta Stone that for a command in here, it gives you the equivalent command in either of these other systems. So in general, I mean, they try to do similar things. And again, I'm going to focus on Slurm just because it's for SciNet at least, and a few other clusters that I have access to, they use Slurm. So I think it might as well highlight this one. Okay, so job scheduling in a nutshell, what it does is basically a tool that will tell the system what to run, for how long, how much resources it will need, and this is done at all times for all users. So I don't want to even attempt to kind of understand exactly all the details that this tool or this scheduler does, but it takes care of a lot of things. So in particular, performs these tasks, which again is assign the user the compute node. So the user makes a request for certain resources, and the scheduler makes sure that the user gets them. Provides some framework to kind of initiate, perform, and then monitor these jobs or this work in the assigned nodes, and also manages the queue of kind of pending work and determines which job will be assigned to the node next. And again, this is done dynamically, right? And if to add to the complexity, there are certain cases in which not all the users have the exact same priorities. Some users may have a high priority because the kind of work they do requires higher priority. So the scheduler takes care of all these different priorities and when to give the resources and so on. And also, again, encouraging fair usage, right? And again, maybe some users have more memory available, more cycles available, so everything on that needs to be taken care of. And luckily, this scheduler does that for us. Okay, so that's what job scheduling is in a nutshell. And just again, focusing here on the Slurm. Here I'm putting some basic commands that Slurm has for us to interact with the system and how to communicate things. And again, this is just a schematic of how these commands interact with some other daemons, which are effectively processes that are constantly monitoring what's going on in the system. And again, these daemons communicate to databases and all the compute nodes and perform all this bunch of stuff. And I'm going to talk a little bit about some of these, mostly about SBatch, and I'm maybe mention some of these along the way. If you're interested in everything that Slurm has to offer you, you can go to the website, which is given in the complete documentation link here. Okay, so that's kind of about the basics of Slurm. Okay, so we're going to start here with our first example, and I'm just going to assume that these lines over here are stored or are saved in a file that I'm calling firstjob.sh. Okay, and here I'm just walk you a little bit for those who have never seen a batch file before. So this is what is called a shebang. This is effectively telling the system that this job, or sorry, these lines are to be executed using bash scripting, which is kind of the one basic shell, a kind of shell script. So okay, so and then the next, what are the next lines? The next lines are called directives, and if you notice, they all start with the hashtag SBatch, which means that the SBatch command in Slurm will take them and do something with them. And in this case, you may have already figured that I'm giving a certain specifications, right? So I'm telling the system what I want. So in this case, I'm as all these names suggest, I'm requesting for 2 nodes, and each of those nodes will have 40 tasks, so 40 cores per each of those nodes. For this amount of time, in this case, I'm asking for 1 hour. And these 2 other things are just things that I want to kind of add other features. In this case, I want to say, how my job I want it to be named. In this case, I'm naming it my first job, and the output. So if whatever output this script generates, it will be stored in a file called job output. And here I have this %J, which effectively will put the job ID. And I'm going to go a little bit about in a second what this job ID is. And here I'm effectively moving to this directory, which is whenever you see in Bash something that starts with a $, is basically an environmental variable. So something is stored in this variable that is the Slurm submit directory. So this is basically some environmental variables that the Slurm has or that the Slurm saves. Basically, in this case, is telling where this particular job was submitted from. And then here, I'm not going to go into too much detail. This is kind of every application will vary, but the idea is to do something in this job with this 80. So you have 40 times 2, that will be 80. So you're going to have 80 processors or 80 cores available to you to do some computation. And then you need to do something with those 80 cores in here. And that's basically the idea of this first job. So, okay, you have that, you save that first job. And then, you simply submit the job again from the logging node. You're going to do something like sbatch and then your first job.sh. Of course, this assumes that this file first job is in the current directory. Otherwise, it won't be able to run. But this is the idea. So just use the sbatch command to submit this one job, and that's it. So these will be sent to the system, and the scheduler will make sure that it will run every single line in here. Well, of course, not these ones, because these are just kind of directives for the system, that's the reason why they are conveniently included as commands. And it will execute effectively every single line after that. So it will do something for you. So for instance, you can do something like your R script in here, and you're gonna try to run R from the command line. Okay, so that's, hopefully that was clear. So if not, okay, no questions. I think hopefully that was simple enough. Even though this is kind of very standard, people don't do this often. I often like it to be a bit more flexible, or give it a bit more flexibility, and luckily Slurm allows you to do that. So instead of doing that, I can alternatively usually do the following. So I'm going to call this file, these lines, second job. And if you notice, it's pretty much identical to the previous one, except that I don't have all those directives in here, right? So I just have, cd slurm, which again, this is an environmental variable set by slurm as soon as I submit the job. And then again, this do something in these 80 cores, which is great. So I personally like this approach better, because now this allows you to submit the job in this following way. So if you notice, it's very similar to the way you submit the job before, except that you are including in the command all those specifications that were previously in the script before. And I'm adding -n to nodes. This is number of tasks per node, 40, time 1 hour, the name, my second job. It's almost, it's kind of almost identical to the previous one. The output in here, and then second job. So I personally like, again, this approach better, because this gives me some flexibility. So for example, what if I don't want to use 2 nodes? What if I want to use 4? In the previous approach, I would need to, change this bash script and change manually the 2 instead of put a 4 in here and rerun. Which in this case, gives you a bit more flexibility into, how to manipulate your request for resources. And if you write your bash script in a flexible way by using these environmental variables or other variables, actually it gives you a bunch more flexibility, and it allows you to change these things as you submit them. You can maybe do some kind of some evaluation. So maybe there are some point where a certain number of tasks, or if you increase the number of nodes, this will run much more faster, and so on. So yeah, again, I personally like the flexibility of this approach. Okay, so okay, what happens? So what happens when you do sbatch? Okay, so if you do sbatch and maybe your bunch of options in here, and then submit the job. So if this is successful, the system will tell you, okay, you submitted this batch job, and this will it will assign an ID number for this particular job. And again, this is the job ID. Okay, that's great. So that's kind of the best case scenario. We did everything correctly. It found the bash script, and it run. At least it's on the queue. That doesn't mean that it's running right away, but the system accepted it as a valid batch job, which is great. Again, you got a job ID in here, or if this doesn't happen, then you may get an error. And there are multiple instances why you may get an error, but some common ones is that the bash script is not executable, and for that you need to change the access or change the the access to the job, usually using this CH mode. And again, this is a bit of Unix shell that effectively change the permissions of this job. In this case, we're giving full permissions to the user, which will be you. Another common error when if this fails is that you are launching from a read-only path. Sometimes you need to make sure that everything that this job will be generating is in a path that is writable. And sometimes this happens because in many systems, when in the compute nodes, you sometimes don't have access to everything in the system. You only have access to a restricted areas, which are oftentimes called like a scratch or are locations that are meant for only being kind of writable only. So you cannot access or write everywhere in the system. So in this case, you need to kind of again move to a writable path. Or sometimes you're requesting for resources that you are not kind of able to allocate. So for example, wall time, memory, cores. So sometimes that's one potential reason why this command may give you an error. But again, could be others. At least I'm trying to list here the most common ones. Okay, so yeah, I want to talk a little bit about partitions. Again, this may not be always the case, but some systems tend to configure they are called queues, different queues or different partitions. And in Slurm, at least, you have access to these partitions using these, -p or -- partition. And so again, administrators usually configure these partitions in separate ways because you may want to have longer wall times. So they are, sometimes called long versus short memory. Long versus short. So which means that in the long partition, you may run a job, for example, up to a few days or even a week, or maybe have no limit. Whereas other queues are intended to do kind of fast computation that the wall time has a maximum of 12 hours. And administrators do those sort of thing to encourage certain or discourage certain other type of users, right? So as an administrator, you may not want people to run jobs for very long, right? Because you are taking over many of the resources. Other reasons that they set partitions, depending on the memory available. There may be queues that are intended to be very memory intensive, right? So maybe most of the nodes in the system may have maybe 120 gigabytes of memory, right? But there may be certain nodes specifically dedicated where you may have 340 gigabytes of RAM, right? So sometimes administrators do that sort of stuff to kind of tailor in a way the kind of jobs that you can run in these partitions. The number of cores as well, for instance, is another feature that sometimes people get to define different partitions for. Okay, so hopefully that was clear. And here switching a little bit on the job monitoring part. So again, there are a bunch of commands that you can use to know what's going on with your jobs. As you submitted your job, and again, as I said before, the fact that you submitted the job successfully doesn't mean that is running right away. I mean, hopefully that's the case, but again, it depends on how many people are using the system, right? How many things are running, and so these tools effectively allow you to check or to monitor whether what's going on. So, for example, if you were to type in the system SQ, it will show you, everything that is in the system in the queue, everything that is kind of getting a ticket or getting a place to start to run. If you only want to see what's happening with the job that you submitted, you use --me. If you specify -j and put the job ID that I showed you before, it will give you specifics on a certain job. You can alternatively use scontrol, which is similar, but it gives you more information. You can get estimates on when a job will run in case it is not running yet. You can cancel all your specific job. You can cancel all your jobs if you change your job ID or your user ID. Of course, in some cases, I think you should use this sort of a command with caution. Maybe you may not want to cancel all your jobs. If you want to look at how a specific partition looks like, you can do that. And again, this account will be information on your recent jobs. Okay, so that's for job monitoring. And something that I want to show you here is that if you're on Signed, again, most of these are kind of command line, and then you see some information in the command line, which may not be as nice. One of the things I really like Signed is the support that they give. And for example, these kind of additional tools that they come up with and really helpful. So for example, this mysigned.useron.ca will give you, very detailed information on various features. It will give you the usage. Actually, if you go right now, just out of curiosity, it will give you kind of the state of the system at how many jobs are currently running and so on, how much data has been used in the Scratch and project, and something that they call burst buffer, which is a kind of like a rapid access kind of space. And this is for the entire system. But of course, if you can also log in if you have an account, and you can look kind of at your history of your job. So you can, what script you submitted, what environment, for how long, and this gets updated on a I guess intervals of 10 minutes or so. So the memory usage, the CPU that you have used, the kind of the gigaflops that you've used, and your input output of your disk. So these are just a couple of images on how this looks like. So if you sign in, again, if you have an account, it will tell you kind of more information on each specific job. And this is the job ID, and it will tell you whether it's running or it's finished, and kind of some of the details. The performance of these jobs, whether or not you are using all the CPUs as they are. You're hoping that you get as your job elapses, you get good CPU utilization, and all across all the CPUs available, of course. That's in terms of job monitoring. Okay, so just switching gears here. I still have a few slides to go. So in terms of CPU, software in HPC. So as you may imagine, right, you have hundreds, thousands of users. They use different software, but you need each of them, you have different needs. You need to be really able to manage or be able to manage your software robustly. And there's this tool called LMOD that actually helps you to achieve that. And usually this is a very nice tool because typically in these systems, you have multiple software that is installed, and you can access many of, each of them using this module command. And effectively, this module command takes care of many things kind of under the hood, sets something that we called environment variables, effectively points the software to the right paths, where to find it, etc. So you don't need to worry too much about that. And it can even take care of kind of conflicting versions of certain software. And this is nice because it's really relevant for reproducibility purposes, because with these module commands, effectively it forces you to specify even which version of the software you are using at a given time. So I think this is a nice tool, that comes with the HP system, because it really allows you to know exactly what version you are running at a given time. So I think that's nice. So some useful commands in this front. So module load, use module name. If you want to use a specific software, if you want to remove all the software that is available, you can just run module purge. And we're going to talk a little bit more on the next slide about this module spider, that this will help you to list what is all the available software, which are similar to this. Module avail is also listing the loadable software that doesn't require dependencies, but that's often not the case in many systems. Often many software requires some dependencies, and module list will tell you, okay, which software is currently loaded in your session. So okay, just again, I'm focusing here on Niagara, and if you are in Niagara in the login node and you type module spider, it will throw a bunch of lines that tell you everything that is installed. So I'm just putting some of a few of the lines. So they have something that they have some stacks. Effectively, these parts are software that either Compute Canada or Niagara kind of administers. And by default, I think this environment is now the default, and you can use it at your discretion. Of course, there are many other lists, and I'm not intending to list everything, but the list is quite extensive. But I want to focus a little bit. I know, I come from a biostats, and I use a lot R. So I just want to show you, if I wanted to do R or use R in this system, how this would look like. So for example, I would type something like module, spider, and then R. Here, notice that I'm not giving anything. I don't know which version. I'm just typing R. And, it will tell, okay, R, and it will identify that, okay, there is something that it finds something that it identifies as R, and it tells me, okay, this is the one that I want, right? Because it's the language, it's physical computing, blah, blah. Okay, great. And it tells me, okay, I have these versions in the system. And, here I'm putting just 2, but it goes from 3.5.3, and there's a bunch of others, and then all the way to 4.1.2. Okay, that's great. So for those, and they also tell me, okay, there are other possible matches. And this is usually funny, and then there are ways to get around that. Everything that contains a small r, it will be listed in here. I cut this list because it was quite extensive. But, all of these are shown here because they have an r somewhere in there. And then it gives you some hints. I mean, if you want other possible matches, do a bit, you can do some kind of grep kind of syntax. And it will tell you, if you want detailed information, you should run it in this way. Okay, that's good. But let's assume that I would just want to load R. Okay, I want to load this version. Let's say that I don't run this, and I careless go about loading the file, loading R. Well, okay, I'm gonna say module load R. I want this version. Okay, it will throw an error, and it will tell me, okay, this cannot exist, but it cannot load it in this way. Okay, you need to still run again this module spider. Okay, I couldn't do that, so I do module spider. Okay, so now the syntax changes a little bit from module spider, and it's telling me a bit more information. So, okay, R, this particular version, and if you read carefully here, it's basically telling me that you need one of these 2 lines to be able to, to be loaded before R for this to work. And the reason for this is because there are effectively within the system, there are 2 versions of R. One version was compiled using what is called the GCC compiler, so the GNU compilers. And there's another version of R compiled using these Intel compilers, which are actually the ones that are suggested by people using, for SciNet. So you can do it, you can load R in these 2 flavors, let's say. And because the chips that are used in the system are Intel chips, I would, more often than not, I would suggest you to use the kind of Intel version. Okay, that's great. So let's do that. So I module load, and then Intel, and then R. And sure enough, this didn't give you an error anymore. And if I were to type R, then I can just start playing with R within the system. So it will, start version 4.1.2, and I can start doing whatever I want with R within kind of the logging node, which again is not recommended, but this is kind of showing you how to access it. Okay, so yeah, okay, it should be fine. So, okay, and then again, I'm focusing here a little bit on R because that's what I tend to use most. Similar things would go about in Python and so on. So for the most part, you can install libraries or packages in, as if you were in your computer. So in this way, if you were to type in here, if you're in a logging node, you can install packages, whatever package you want. And more, for more likely than not, it will install them. And there are some exceptions to this case. And it sometimes happens that certain clusters have no internet access, or sometimes only the logging node have internet access. So the way to go about here is that, in a system like SciNet, you kind of make sure that all the packages are installed, before going and doing some computation. So before submitting a job, make sure all your packages are installed by installing them in the logging node. There are certain clusters that have no access to the internet whatsoever, not even in the logging nodes. Those are a bit trickier because then those force you to effectively download all the packages either in source code or in binary, and then upload it to the system, and then install manually each of the packages and their dependencies, kind of one at a time, using the file interface for you. Maybe some of you have done that before, installing packages not from the internet but from an actual source file. So it is possible, but it's a bit painful. So yeah, I've come to clusters that have no internet access, and yeah, that's what you have to do. And there are some other exemptions to, when these may fail, is that the installation of certain packages actually requires some special dependencies. And that's what I wanted to talk a little bit about in the next slides. So for example, I want to install data table, which some of you may be familiar with this package. And if you have read, or if you're more familiar with data table, has this feature where you can use something that is called OpenMP or OpenMP support, which effectively allows you to scale data manipulation much more efficiently because you are using all available cores that in your system. So by default, probably you may already know, R only works on one single core. It doesn't come knowing kind of all the cores that are available in your system. So okay, how you would install data table using this OpenMP support? Okay, so I'm again in my login now in Niagara, and I would go about something like ML is just short for modulo before, and here I'm, oh, this shouldn't be repeated. This is only one ML. Sorry, there's a bit of a typo. But I'm gonna load, now notice that I'm not loading the Intel version anymore, but I'm loading the GCC compilers, and that's because I need this OpenMPI additional module for this to run. And again, 4.142, and then I start R, and then I want to install data table. Okay, I could install data table, close it, and it will run. However, the version that I would install, if I were to do that, it wouldn't come with OpenMP support. So what I need to do, so I need to tell the system where to find certain libraries and directories that are required by data table at compilation time. And these are only loaded by, again, adding this OpenMPI and telling the system where to find them. In Signet, that's relatively simple. That's not always the case in every cluster. It's telling you, okay, where to find the include and where to find the libraries. And this is effectively what you would run. So you're adding some configuration arguments to the install option. And if you run it like this, actually will run. And if you do library, actually tell you, okay, library data table will actually run with 20 threads, which is what you would expect. If you've run this without OpenMP support, it will give you a bit of a longer text. You may have come across it that effectively tells you, oh, it's only running with one core, and that's it. But yeah, in this case, you're able to do it with taking care of 20 threads, which is great. Okay, so that's that. Maybe just want to reaching almost time. So just want to here's some points on data creation. The takeaway message from data creation is that try to reduce as much as you can generating multiple small files. Try to always try to write to the fastest memory that you can, which will be RAM, and then cluster everything in there and put it outside in your long-term scratch system. So I'll let you one more, a few more seconds to run that, but that's the bottom line. That's the idea. So, and if you can write data in binary, so that's also a good take-home message here. In terms of data management, how to organize the files, maybe there's no many surprises here. Try to avoid very long names with human interpretable names. Maybe a better approach is to run use metadata, right? So how to have a well-maintained database on your files, although that's, there's some need some tools perhaps to do that. Of course, organize your information in directories and subdirectories. Never throw everything in the same directory. Yeah, and of course keep back up your data. I think that should be very well, like a no-brainer. But yeah, okay, maybe 1 second there. Yeah, just as a take-home message for the entire workshop, hopefully I convince you that HPC can really accelerate your work. But understanding how to operate and how to make efficient use of this HPC system is crucial. And of course, that's hopefully I give you some pointers to do that today. I'm putting here some acknowledgements. So some slides actually were very helpful. Took it from some of these talks where you can access to. I think they are available. There's some intro to shell and cluster computing. And the one thing that I really want to highlight is that SciNet runs very nice education classes and even certificates. So I really recommend you to have a look. And if you don't have an account, probably some of the faculty members or investigators that you collaborate with, they probably have an account. So look for them, and if you can have access, request them to grant you access, so you can have access to these education sites and courses. Some other clusters. So again, you may not be at U of T, but many of the hospitals around the area, Compute Canada has other clusters, and so many other hospitals in Toronto have their own computing systems. And in case you're interested, there are also some topics of some links here for how to do things in R, which again is what I use most. Sorry, I'm running out of time here. Thanks for listening. Thank you.
Thank you, Osvaldo. So while you were presenting, I actually received an email from SciNet with all the list of all the education courses that they're offering this term. So I think you can go on their website too and see what courses they're offering. Yeah. Great. Does anybody have any questions for Osvaldo?
Can I ask a short question?
Sure.
Okay, so my question is, how can we actually predetermine for example, the number of nodes we require or the time limit we want to set? How can we predetermine those parameters?
Yeah, I think this is a really great question, and it doesn't have like a really straightforward answer. But I guess my suggestion would be to start simple. So start with. So I think there are typically two kinds of problems. So problem that is referred to as embarrassingly parallel problems, which effectively they are very easy to scale up. Things like in the case of statistics or biostatistics, something like simulations tend to be embarrassingly parallel because the time between iterations effectively is very similar, right? So you don't expect too large deviations between two replicates from the same set of simulations, right? So those are very easy to parallelize and to scale, and the more cores that you throw at it, you can scale very nicely. So you have a very good sense of how long your job will take by maybe by starting with a few hundred replicates, right? And see, okay, if a few hundred replicates take whatever amount of time, so you start scaling from there. You just multiply, and that's super easy. Where it gets a bit trickier is for those problems where this is not really the case, where you have things like different balancing, that maybe one particular instance will take a lot of resources and take longer time. So those are trickier, and those we probably need to do a bit of maybe clever ways to try to make them more kind of stable or more similar across the potential jobs, or you do very good prototyping and kind of understand what the problem is and do a good guess. So I think those I'm usually more familiar with the former one, so that's why it's not that hard to start kind of simple and then start, okay, how long it will take me to do this many, and then you just kind of multiply accordingly. So having a good way of tuning or assessing how long one instance will take or a few dozens already gives you a good idea of how long the entire thing will take. Yeah. Hopefully that makes some sense.
Yeah. Okay, I got it. Okay, thanks so much for your answer, and thanks so much for your presentation. Yeah, it's very helpful.
My pleasure. Yeah.
Hi, Osvaldo. Thank you for the great presentation. I actually have one question in regards to when you mentioned about the run the parallel and try to save your parameters in the metadata. So could you give a little bit data example for that because I'm always like learning about fire management.
Yeah. I think I admittedly I don't think I do it as much as I should, but I think the idea is to sort of generate, for example, a file that contains well, say your parameters, right? Let's say you run a simulation with a few parameters. So you have a file that effectively contains all the instances, right? So all the potential combinations. And then out of that, you have an index. You can number them 1 to 20, right? Something like that. So instead of saving each file name kind of simulation, parameter 1, parameter 2, 3, parameter. So you just your outputs are just going to be output 1, 2, 3, all the way to whatever number you have. But you have, that's kind of the metadata, right? So in the metadata, you know what the output 300, for instance, you know the configuration that you run for that one, as opposed to have a very long name with all those parameters kind of in the file, which I guess it could be helpful, but maybe from the file system perspective, they take longer to to even process, right? Because you have these very long names. I think.
I see. Yeah, I think I did exactly what you said, like having very long names for each parameter.
Yeah. Which again, admittedly, I tend to do, and it's probably about practice and something that I will definitely need to change. Yeah.
Well, thank you. Yeah.
Thank you for the question.
Well, I guess I'll just add a comment that there's actually like a restriction of what the number of clusters and nodes each account can specify. So every account has its level. So if you're a student account, it'll be like the basic level that you request for resources, and in different computer clusters have different thresholds. I believe for Cyanide, it was like 30 clusters, and for like the HPC at SIG kits, I think it's capped at 20. I don't remember the exact number, but it will be showing up on the document. If you request more than what your account is allowed, the program will likely won't run. And also, if you request to the max capacity of your allowance, you're going to wait a long time, because there is an algorithm in the back whose job gets to execute it first. So if you request a lot of memory, it's very likely you get put at the bottom of the chain, the food chain. So it's an art. So it's kind of like people try a few settings and then realize, okay, 2 gigabytes of memory is probably the ideal ones to speed up the queue lines.
Yeah. I think what you're mentioning, it's really important, because you're right. It's a bit of there's always trade-offs. So you want your job to finish as soon as possible, right? But maybe that if it will run for 5 days, you will have it, right? But of being realistic, you cannot take all those many resources for 5 days straight, right? So how can you kind of you can either throw more cores at it for shorter time. So there's always a balance between the number of cores that you are throwing at the problem and the memory. So you need to be very mindful of those sort of things. And oftentimes what happens is that you have some allocations per night or per cycle per day. So if you exhaust all the resources per day, you're right. So you're going to be at the bottom of the queue for that day. But often, well, at least on Cyanide, the way it is that if you for the next day, you'll probably be fine. But unless you use a lot of resources on the one day, and then for the next few days, you're gonna still be kind of on the low end of the queue. So yeah, all those sort of things do matter when you are scheduling for jobs. Absolutely. So yeah, I guess you want to be clever, and you can maybe even use more than one system. I mean, sometimes that's also helpful. But yeah, so that's a great point. Any other question, comment?
Yeah. Any other questions?
Thanks.
Well, if not, yeah, thank you, Osvaldo, for a very great introduction to Niagara and SciNet. Hopefully, we'll have more workshops about high performance computing, and maybe we can have one dedicated to running simulation studies, because I feel like we usually tend to use to SciNet for running simulations in parallel.
Yeah, absolutely.
Yeah. Okay. Great. So thank you, everybody. And our next workshop will be February I think 21st, no, 28th, right? What were we gonna do, Kwon?
The plan was to have Matt to do some data visualization.
Right.
So the tentative plan is to do fancy ggplot or ggplot ready for publication.
Okay.
But we'll finalize that soon.
Yeah, and you'll receive communication about it. Okay. All right. See you, everybody. Thank you.
Yeah.
Thanks, Osvaldo.
Thank you. Thanks, everyone.
Thanks, Osvaldo.